So, have you ever stared at a physics problem that looks kind of simple, but then just completely ties your brain in knots? Well, today we're going to unravel one of those classics. It's a mechanics problem about two springs connected in series, and it comes from a book that has been challenging physics students for decades. Yup, this one comes straight from Irodov's Problems in General Physics. If you've heard of it, you know this book is legendary for its mind-bending problems. So if this one seems tricky, you're not alone. But that's what makes it so awesome to solve, right? We're going to break this down step by step so you can really master the concepts behind it. All right, here's our game plan. First, we'll look at the problem exactly as it's written. Then, and this part is super important, we're going to talk about a really common mistake so you can avoid it right from the get-go. After that, we'll dive into the real physics, derive the formula we need, calculate the answer, and then wrap up with the big takeaway you can use for other problems.
Okay, let's roll up our sleeves and get to it. First things first, what are we actually trying to figure out here?
Okay, problem 1.129. We've got two springs, right? And they have their own stiffness, K1 and K2. The most important phrase here is connected in series. So just picture them hooked together, end to end, kind of like a little chain. Our job is to figure out the absolute minimum work needed to stretch this whole chain by a total amount, delta L.
Now hold on. Before we write down a single equation, we have to talk about a trap. It's a mistake that feels so intuitive and so right, but it will lead you down the wrong path every single time with this kind of problem. You might be thinking, hey, I've got two springs, I'll just add their stiffness values together. So the total stiffness is just K1 plus K2. Makes sense, doesn't it? But nope, that is the pitfall. For springs in series, it absolutely does not work that way. And here's why. That simple addition, K1 plus K2, is what you do when springs are in parallel, when they're next to each other, both attached to the same object and sharing the load. But our problem says they're in series, end to end. One pulls on the other, and that changes the physics completely. So, if we can't just add them up, what's the right way to think about this? We gotta go back to the basic principles. Let's really break down what happens when you pull on this little chain of springs. What's the force doing, and how is each spring stretching? Okay, here's rule number one, the absolute golden rule for anything in series. The force on each component is exactly the same. Think about it like a tug-of-war. The tension in the rope is the same everywhere along its length, right? It's the same idea here. The force you pull with is transmitted all the way through. So the force F on spring 1 is the same as the force F on spring 2. But, and this is the really cool part, while the force is the same, the stretch is not. This is the key. The spring with the lower stiffness, the floppier one, is going to stretch a lot more than the stiffer one, even though they're feeling the exact same force. So to get the total stretch of the whole system, or delta L, you just add the stretch of the first spring to the stretch of the second one. And that gives us this beautifully simple equation. The total extension, delta L, is just delta L1 plus delta L2. It looks almost too simple to be useful, but trust me, this little equation is the key that unlocks the entire problem. Okay, so we've got our two foundational ideas. The force is the same, and the stretches add up. Using just those two things, we can now figure out the overall stiffness of the system. We're going to calculate what's called an effective stiffness. We'll call it K effective, which lets us treat this whole two-spring setup as if it were just one single spring.
Let's just walk through this. Step 1, we start with our stretch equation. Delta L equals delta L1 plus delta L2. Step 2, we use Hooke's law. You remember Hooke's law, right? Stretch, delta L, is just the force divided by the stiffness, F over K. So we substitute F over K for every delta L term in our equation. And here comes the magic. Since we know the force, F, is the same for everything, it shows up in every single term, which means we can just cancel it out. Poof! And what we're left with is this really elegant relationship between the reciprocals.
Now we just do a little algebra to solve for K effective, and we get this nice, clean formula, the product of the stiffnesses divided by their sum. And here's a super useful trick to check your work. For springs in series, the effective stiffness is always less than the smallest individual stiffness. You can think of it like a chain being only as strong as its weakest link. Here, the system is always softer than its softest spring. So if your answer for K effective is bigger than either K1 or K2, you know you've made a mistake somewhere.
We're on the home stretch now. Seriously, the hard part is over. We took this kind of complicated two-spring system and figured out how to treat it like one simple spring with a single effective stiffness. Now all we have to do is use that to calculate the work.
To do this, we use the work-energy theorem.
Basically, it just says is the minimum work you put into stretching the springs gets stored as potential energy in the springs. It's like when you wind up a toy. The work you do turning the key is stored as energy in a little spring inside, just waiting to be released. For us, it's simple. The work we do equals the potential energy stored.
And we all know the classic formula for spring energy, right? It's 1/2 kx squared. Well, for our system, the k is just our k effective, and the x, or the stretch, is our total delta L. So we just plug our formula for k effective right into the energy equation. And boom! There it is. That's the answer to the problem. That whole expression tells you the minimum work needed.
Awesome, we did it. We solved the problem. But let's not just move on. What's the real lesson here? What are the core ideas that you can take from this one problem and apply to tons of others?
These are the golden rules for anything in series, not just springs. Number 1, the force is the same everywhere. Number 2, the displacements, or stretches, add up. Number 3, as a result of that, the reciprocals of the stiffness add up. And finally, number 4, the whole system is always softer, less stiff than its softest part. If you can burn these 4 rules into your brain, you'll be ready for any series problem they throw at you.
And that leads to one final thought for you to chew on. We've totally picked apart the series problem, but what if those springs were hooked up in parallel instead? Which of our golden rules would change? Would the force still be the same, or would it be the stretch? And how would that change the effective stiffness and the final answer for the work? Go ahead, give it a shot, because working through that question is the absolute best way to prove that you've really mastered this stuff.